Hello, hello. Hello and welcome. I'll just do a very, very brief intro to allow us to get on. I just want to say a few words. It's great to see so many familiar faces. My name is Artur Garces, and I was talking to someone. We can do without the mic. I guess that's for the recording also, but yeah, thank you. I was talking to someone the other day about NeSy, and they were saying, well, you were ahead of the curve. This is already the 4th edition. And I had to say, no, it's actually the 17th edition. And we started back in Edinburgh in 2005 at EGCI. Some of you may have been there. And I was thinking about the first ever event. Pascal Hitzler, who couldn't be here, was a co-chair with me, and And of course, we had 2 keynotes, Ron Son and Stefan Hudober, who unfortunately passed away much too young earlier this year. So rest in peace, Stefan. We are doing this workshop in your memory. He made great contributions, fundamental contributions that were then used by many other systems, the CHCL system and his core system that was then used by many others. And he was a keen Neural-Symbolic AI enthusiast. So I'll just allow Marco Gori to say a few words, and then we'll get on. So thank you all for coming, and yeah, I hope you have a good time. Marco.
Just for thanking the people from the organization, who have offered a lot of efforts for the meeting. And the other important thing for you to know is that at least for today, this afternoon, there is a parallel workshop on, organized by the Siena Artificial Intelligence Foundations, where there are mostly at this time companies discussing on ethics and artificial intelligence. And it's important for you to know that also at dinner they will be together, so there will be the opportunity also of discussing not only between scientists but also with people from companies. And of course you will stay also in the next 2 days, and you can take the opportunity of let's say having this cross-fertilization between research and companies. So thanks a lot for coming. And I was talking with Artur about the risk we took of organizing for the first time NeSy offering a specific place instead of the umbrella of the International Joint Conference on Artificial Intelligence. So pleased to see that there are so many people coming. So thanks a lot, and I wish you a very nice workshop.
Okay, my name's Tarek. I'm the general chair of this year's NeSy. Also from my side, a very warm welcome. Being general chair means I'm in the privileged position where I can criticize everyone, but I actually don't really have to do any work. So the people who really brought this together are Artur, who's also one of the founding fathers of the community, Marco, our very kind local host, and Ernesto, who basically did it all, plus a very engaged team of local voluntaries whom you will see moving around whilst you're here. So also from my side, thanks to all of you, because you make this happen. And General Chair also is the honorable activity of saying thank you to a couple of company sponsors. So this year's edition got kind financial support from Sony AI, from Google. We got support from iOS Press, where there also is a dedicated Neural-Symbolic artificial intelligence journal at the brink of launching. So in the future, if in the past you have the feeling that you don't really know where to send your NeSy contributions, there will be a venue where people are specifically looking for it and specifically looking at it. with an integrated view. Obviously, this amazing site is full or partial, but definitely property of the Università di Siena. We got kind support from the Artificial Intelligence Journal, and everyone who registered and is not currently taking a free ride, you probably paid via a website of City, University of London. So also there, thank you to all of these institutions. And as I said, now handing over to someone who actually worked for it.
I don't want to risk to... Okay, so it's not completely true. Like, I mean, I've been working hard, and probably you know me because I was trying to chase all of you to finalize the proceedings, which hopefully will be out very soon. But I would like to say a big thank you, apart from all the organizers and sponsors, but also you, the authors, the attendees, and also all the PC members that make this workshop possible. And this year we have like a clear winner for in terms of authors and PC members. There's Italy. It might be biased, because it doesn't count the weight or how many papers, but then the number of authors. Maybe if there is one paper with 100 authors from Italy, that's why they're the winners. But also, I think thanks to the local organizers, I think that makes sense. Like we also bring the Italian community to NeSy. Just to give some statistics of how we did the reviewing process, we got like a very nice number of submissions, 41. I think it was record in recent years. And of course, we couldn't accept all the papers, unlikely. But we got hopefully you got good feedback, at least 3 reviews per paper, and we also tried to keep like a low load for PC members. This year we also have a track for recently published papers, which actually was quite successful. We didn't expect so many submissions. So again, we couldn't accept everyone. I think we did like a light review depending on the topic and the venue, and also in the terms of the space we need to cut. So unlikely we couldn't accept everyone. Proceedings are on the way, and now we have the pre-proceedings out. But yeah, big thank you to the 60 PC members plus 4 reviewers who also helped us on shaping up the program. Apart from Mark, I would like to also thank you all the local organizers who were supporting and during the way and also today. So thanks a lot. So yeah, big thank you for everyone. And I don't gonna steal you much more time. So this we updated the agenda a bit because we started a bit late because of the problem with the mics. The biggest change is that the poster pitches are going to be after the coffee break. And then the key is if you could do in the coffee break already set up the posters, it would be fantastic. But that was the change. And then since we have one hour between all the sessions and dinner, now we have only half an hour. The only thing we do apologize. But yeah, I think now is another thing is
we have one very final slide. Many of you, I assume, already know that. But a few months ago, we also set up a community Slack. So we have at around 600 people live there. If you do not yet have it, but you're a Slack user and you occasionally just want to keep an eye on where are open positions, what are call for papers, or also you just want to pitch an idea, want to get feedback, that's your Slack group. I think the login link should still be valid for 21 days. If it doesn't work for you, just send an email, ideally to Arthur, me, or Pascal Hitzler, and we'll put you live. Okay, enough from us. Now for the actually important people, and we are very happy that we can have an esteemed guest in our midst. But, Eleonora, over to you. Do you want?
No, just leave it. Okay. So, hi everybody, I'm Eleonora Giunchiglia, and today it is my honor to introduce to you one of the greatest researchers in the field of AI, Professor Yann LeCun. Today, Professor LeCun will be presenting his talk titled Towards Machine That Can Learn, Reason, and Plan, in which he will share with us his visionary insights into the future of AI. Before getting into his talk, though, I would like to give a very brief introduction and provide you with a glimpse into the remarkable achievement of this professor. Professor LeCun, as you all know, is a world-renowned computer scientist and a pioneer in the field of deep learning and neural networks, so much so that he is widely recognized as a founding father of deep learning. Currently, he serves as Chief AI Scientist at Facebook and the Silver Professor of Computer Science at New York University. Throughout his career, Professor LeCun has made significant contributions to the development of machine learning algorithms and methodologies. For example, everybody knows convolutional neural networks that have revolutionized the field of computer vision, enabling machines to achieve incredible performance in image recognition and object detection. Professor LeCun has been widely recognized and acknowledged. He has received numerous prestigious awards, including the Turing Award in 2019, which is considered the highest honor in computer science. In conclusion, Professor LeCun's contribution to the field of AI has laid the foundation of modern deep learning and continues to inspire researchers and practitioners worldwide. We are honored to have you here today, and please join me in giving a warm welcome to Professor LeCun.
Thank you so much. Okay, the troubles with audio shows that we're probably going to have human-level AI before we get audio and video that works. Yeah, that's going to come. Okay. Okay, so for those of you who heard my talk earlier before lunch, I have to apologize because it's going to be a little bit of overlap, but this is going to be more technical, hopefully. Okay, so objective-driven AI. There's a lot of talks today, of course, about like the progress of AI. But I'm just throw some cold water on this, like I did this morning, saying that plainly and clearly that machine learning sucks, in the sense that we do not have machine learning systems at the moment that can rival the performance of what we observe in biology in human and animal learning. So humans and animals are capable of learning new tasks extremely quickly and sort of reuse their background knowledge about the world from one task to another, which is what perhaps we call common sense. And this is the type of capability that we are not still able to reproduce in machines. So one way that to kind of bridge this gap, is to get machines basically to understand how the world works, to predict the consequences of their actions in advance, to be able to perform chains of reasoning, which is really what this workshop is all about, with an unlimited number of steps, and to plan complex tasks by decomposing them into simpler tasks, essentially. Hierarchical planning. And a lot of this is predicated on the idea that we're going to be able to get machines to learn without being supervised, without necessarily being reinforced. And this is kind of a form of learning I've been advocating for a long time called self-supervised learning. And really this has taken over the world. So, I like the audio in this room. Okay, here we go. So SSL really has been taking over the world. Unfortunately, not so much for vision yet, but certainly for text, because it's much easier to make it work for discrete data than it is to make it work for continuous data. But the basic idea of SSL is that you're not training the system for a particular task, you're training a system to represent the world by capturing the mutual dependencies between the various parts of the input. So a typical example would be something like video prediction, where you show a piece of video to the system, and you hide part of that video. It could be the future of that video, it could be the past, it could be the left half, doesn't matter. And then eventually you reveal the rest, and you train the system to predict, or at least capture the dependency between the thing that it observes and the thing that it doesn't yet observe and eventually observes. So this kind of idea of self-supervised learning, or this particular formulation of SSL, has been incredibly successful in the context of text. LLMs are a special case of an older idea, which is to train a system to represent text by essentially predicting missing information. So you take a piece of text, typically a few thousand words or a few thousand tokens, subword units. You mask parts of it, typically 15% of the words or something like that. You replace them by blank markers, and then you train some gigantic transformer network to predict the words that are missing, right? And in the process of learning to do this prediction, the system learns a representation of text that allows it to fulfill the task. And that turns out to make it necessary for it to learn grammar and syntax and semantics and meaning and everything. So that's been incredibly successful. The combination of transformer architectures plus self-supervised learning of this type, which is a generative type of self-supervised learning, it's actually a special case of what's called denoising autoencoder, which is a very, very old idea, going back to the 1980s. But it's really very powerful in many ways. And it can be applied to other things than just text, but it's very successful for text. So that goes back to 5 years with the BERT paper, and then a lot of follow-up work, which really revolutionized natural language processing. Okay, so generative AI, in the case of text in particular, is a special case of this where, and in fact it's been used not just for text, but also for images and video, but it's a special case in which the masking only applies to the last word or the last tokens, right? So you take a window of text, you mask the last word, and then you train the system to predict this last word. Of course, you cannot make this prediction exactly, so what you do is you train the system to produce a probability distribution over all the possible words in the dictionary, all the possible tokens, and that's easy to represent, right? Because we know how to compute softmax, exponentials, and normalizing. So you get a bunch of numbers between 0 and 1 that sum to 1 that supposedly represent the estimates of the distribution of the next word in the dictionary. And of course, once the system is trained, you can use it to just produce text by autoregressively injecting the predicted word into the input of the system and then predicting the next word, injecting this into the input, shifting it, etc. Right? Autoregressive prediction is a very old idea, going back to the 50s or something. Not in the context of text necessarily, although yes, n-grams go back to Shannon, so that's really old. So this works surprisingly well for if you train on enormous amounts of data, like typically 1 to 2 trillion tokens, with models ranging from 1 billion parameters to 500 billion, or maybe even 1 trillion. And there's been a number of language models like Blunderbot, Galactica, etc. And then, you know, ChatGPT, GPT 1, 2, 3, 4, ChatGPT, which is fine-tuned, Chinchilla from DeepMind, Lambda and Bard from Google, and then more recently Llama from FAIR, which is open source, and Alpaca, which is a fine-tuned version of Llama. And then a whole bunch of models that are being fine-tuned. What distinguishes the models from Meta is that they tend to be open source, although at the moment the license is somewhat restrictive, but that's not going to last. So the performance of the system is amazing, but they make really stupid mistakes. They make factual errors, logical errors, they are inconsistent, they have very limited reasoning ability, there's no way to control them for toxicity and things like that. They have essentially very limited knowledge of the underlying reality because they are purely trained from text, and they certainly have no real common sense in the way that we would understand it. And they don't really have any ability to plan, although they work surprisingly well for fully observable deterministic environment like code. So it's easy for an LLM to predict what the state of a program, the memory locations for a program is going to be because it's fully observable. So they work surprisingly well for generating codes in various languages. They can generate text, although if you ask them to generate hallucinations, they will. You know, I never actually produced a rap album. but it's going to be happy to write a critique of my last rap album. And you can coerce those LLMs to do things that are really stupid. Like you try to convince them that 4 and 4 equals 2 plus 2 equals 5, and they'll say, oh yes, I'm sorry, 2 plus 2 equals 5 indeed. So what are they good for? They're really good for writing assistants, for draft generation, for stylistic polishing, certainly for code writing, at least assistants. But they're not really good for producing factual and consistent answers because of this hallucination or confabulation problem. Taking into account recent information, you have to retrain the system completely if you wanted to learn about yesterday's New York Times. That's too expensive, so it doesn't happen. For behaving properly, reasoning, planning, doing arithmetics, using tools. So this is called extended LLMs. LLMs that can use tools like search engines, calculators, simulators. There's no clear way to do this. There's a whole bunch of attempts, but no kind of globally accepted recipe. So we're easily fooled by their fluency into thinking that they are intelligent, but they really are not. I mean, they have some level of intelligence, not the type of intelligence we expect from animals and humans. There's another major flaw, which is that the fact that they produce tokens autoregressively one after the other. If you imagine that there is some sort of average probability E that any token generated takes you outside of the set of correct answers, then the autoregressive prediction process is basically an exponentially diverging process that will take you out. It's basically a diffusion process, right? It will have a exponentially decreasing probability of staying within the subset of responses that are correct for a particular prompt. And this is due to the fact that the answers are not planned. They're generated one token after the other. So they really are not that great. My main beef with them is that they don't understand the real world, only through text, and text only represents a very sort of simplified model of reality interpreted through humans who wrote the text. And so one big question is, how do we train those systems to understand the world the way animals and humans do? Animals, all the animal knowledge is non-linguistic, right? And even most of human knowledge is actually non-linguistic, depending on how you measure the quantity of human knowledge. So I think that's a big challenge. Other limitation, which I think is more interesting to this community, is that those systems really have very limited abilities to plan. And there's papers from various kind of chapels, if you want, in AI. So people from cognitive science, say those systems really can't reason. They manipulate language, but language is different from thought. And so those systems do not think. They are fluent, but they manipulate language, but they do not think in the way that humans and animals do. And then people coming from a classical AI saying, classical AI has been interested in the problem of planning and search for decades, and those systems really can't do it, at least not to the extent that we'd like them to. So I think there are 3 challenges for AI and machine learning going forward. One is learning representations and predictive models of the world, and I'll come to this in a minute. And this is going to probably happen through this idea of self-supervised learning. Learning to reason, this is really the topic of this workshop. So basically getting machines to be like, Daniel Kahneman's System 2. I mean, he didn't invent the concept, but he's been kind of popularizing this idea that there is tasks that humans do for which they deliberately, consciously use their entire mental power, if you want, to do it. So this is System 2, and then System 1 is the kind of tasks that you do without thinking about them subconsciously, essentially. And autoregressive LLMs today, and most AI systems today, are System 1. They produce answers reactively. There's no planning in advance. So how do we get system to do System 2? And this is why I think a lot of you here are motivated to work on neural-symbolic systems. I either agree with you or disagree with you, depending on what you mean by symbolic. For some definition of symbolic, I agree. And then the last thing is really kind of related to number 2. It's learning to plan complex action sequences. So a little over a year ago, I posted a paper on Open Review called A Path Towards Autonomous Machine Intelligence. And people got spooked by the idea that machines could be autonomous, so I changed the name now towards objective-driven AI systems, explaining that those are systems that can learn, reason, and plan, but they do this to satisfy an objective. I gave several technical talks on this. One of them is at Berkeley, but it's a bit old. There's a more recent one that I gave at Northeastern University, which is basically another version of the talk you were hearing today. Maybe slightly less technical, actually. So the way I am proposing to approach this problem of allowing machines to learn and plan is through an architecture. People used to call this cognitive architecture, which is centered around this idea of world model. So what is a world model? A world model is a module that allows intelligent agent to imagine how the world is going to evolve, particularly imagine how the world is going to change as a consequence of its own actions. And if you have such a world model, then you can imagine a sequence of actions that will satisfy a particular goal. Okay, that's planning, really. That's really what planning is all about. So the components you need in that cognitive architecture is the world model, really the sort of centerpiece of it. A cost, so the cost module is something that defines the goals. Okay, so think about something that just computes a scalar value that indicates the degree of incomfort of the machine, and the entire purpose of the system is to figure out a sequence of actions that will, according to the world model, result in a state of the world that will minimize the cost. Okay? So the system imagines a sequence of action through its actor, runs that sequence of action through its world model. The world model predicts an outcome, state of the world, runs this through its cost function, and then the cost function tells it, yeah, this is a good outcome or a bad outcome. Okay? And so the entire purpose of the system is to, through some optimization process, figure out what is the best sequence of actions that will minimize this cost. And I'm not talking about learning, I'm only talking about inference. Okay? I'm assuming the system has been trained. This is occurring, this optimization process is occurring at inference time. All right? And that's reasoning. Call it Neural-Symbolic if you want. I'm not sure actually it fits in your definition, depending on who you are. But that's the thing. So the perception module is there to give the system an idea of the initial state of the world, the current state of the world, perhaps combined with the content of a memory that perhaps contains the knowledge about the world that you don't immediately perceive. Okay? And forget about the configurator for now. I might talk about this later. So the general process is something like this. Observe the state of the world, run it to the perception system, gives you an idea about the initial state of the world in an abstract representation sense. Combine this with a memory that contains the previous imagined or perceived state of the world. Run this to your world model and hypothesize an action sequence that you feed to your world model, and your world model is going to predict an outcome for that action sequence. A predicted state sequence representation. You feed this to objectives, and there's two kinds of objective. One set of objective is the task being fulfilled? Am I answering the question? Am I fetching the object I'm supposed to fetch if I'm a robot? Am I kind of satisfying the goal? And then there is another set of objectives that are essentially guardrails. So there are objectives that are there to guarantee that the system is safe. So if you're worried about, telling a machine to produce paper clips as efficiently as possible, and you're worried that it's going to take over, transform the entire galaxy into paper clips, you can put guardrails objectives to prevent this from happening. Unless you are really, really, really stupid, like an Oxford philosopher. Obviously, this may involve having a world model that can sort of make sequential prediction of multiple states. So you take not just a single action, but a sequence of actions. And every time you run your world model to predict what the result is going to be. You can apply your guardrail cost at every time step and to guarantee that nothing really bad is going to happen. And then measure the task cost at the end. And then through some optimization process, possibly gradient-based, possibly gradient descent, backpropagate gradient from the cost through the world model all the way through the action and find a sequence of action that minimizes the objectives. Now, that assumes that the objectives are differentiable, and the world model is also differentiable, okay? If they're not differentiable, then it's harder because you're gonna have to do some combinatorial search optimization to figure out the optimal action. So for example, if you're playing chess, you don't really have a world model other than the actual board, and that's not differentiable. Your cost function is not differentiable either. It's whether you win or lose in the end. Okay, so now your search is gonna have to be combinatorial and discrete. And you're gonna have to use, Monte Carlo tree search or something like this, right? Not very efficient, but inevitable sometimes. This is the kind of planning that humans are actually pretty bad at, okay? The kind of planning we're really good at is situations where the costs are differentiable, the world model is differentiable. So typically kind of motor control type situations. Now, of course, the world is not deterministic, and not entirely predictable. So probably what you're gonna have to do is have a world model that has a set of latent variables as inputs. If those latent variables are just random things you can't predict, you can draw those latent variables through some sort of distribution. And then you have to do your planning to protect against bad things that could happen. So do the planning multiple times for several drawings of that latent variable, or do some other methods. Or perhaps the latent variable are due to the fact that you are in an adversarial situation where you're playing against a nefarious opponent, and then you have to basically do a reverse optimization with respect to the latent variable, which would be kind of, what is the action the opponent can take that will maximize my cost, right? That's a typical game situation. Now, what you really want is something that's, a hierarchical version of this, because we, as humans, we do hierarchical planning absolutely all the time. We don't realize it because we take it for granted, but we're extremely good at this, and animals are also very good at this. Just, not with the same level of abstraction. What do I mean by this? So I gave this example earlier this morning, but let's say I'm sitting in my office at NYU and I want to go to Paris. I cannot possibly plan my entire trajectory from my office at NYU to Paris Charles de Gaulle with millisecond by millisecond muscle controls, right? That's impossible. This is the kind of planning that robotics does at the moment, but you can't do this for complex tasks. What you do is you decompose it into simpler tasks, and you have a representation of the world that's much more abstract, at a high level of abstraction. So much of the details are not present in the representation. So the first thing is, okay, if I want to go to Paris, I probably got to catch a plane, right? Which means I have to go to the airport. Should I go to the airport by taxi or by subway? Should I go to Newark or JFK? There's a bunch of questions you might answer like this, which are sort of discrete choices if you want. Once I get to the airport, which airline am I going to catch? But basically, the first action I need to do is go to the airport. Okay, so the output state of the first predictor is, am I at the airport? Okay, the state vector here represents basically that I am at the airport. And that constitutes a goal for the lower level planning that needs to now minimize my distance to the airport. Not to Paris anymore, to the airport. How do I get to the airport? I need to go down in the street and grab a taxi or take the subway. Okay, so again, I've decomposed this into two subtasks that are fairly simple, represented at a high level of abstraction. How do I go down in the street? I need to get out of the building and hail get out of the building. Basically go to the elevator, take the elevator down and go down on the street. How do I get to the elevator? I have to stand up from my chair, go to the door, lock my door, etc. And then you can imagine sort of, making this kind of decomposition all the way down to millisecond by millisecond muscle control, which, will allow you to step up from your chair, which is the first action you have to take. So that's the idea of hierarchical planning. There's no AI system today that is able of doing this, as far as I know. Perhaps you guys have some idea. Or at least there is no AI system that can do this, where the various levels of representations are learned, and the world model is learned. Okay? You can hardwire this. So for example, if you have a legged robot, and you tell the legged robot to go to the kitchen, you have a map of the house with obstacle occupancy map. So the system can plan a trajectory to go to there, and then call a lower level planning to actually plan the motion of the legs to get to the right location. That's hierarchical planning, but it's completely handcrafted. It's the motor control equivalent of what people were doing in computer vision before 2010, where they would handcraft all the feature representations at every level in a recognition system. Okay? What we like to do is learn those representations. The same way a convolutional net can learn hierarchical representations of perception, what we need is a system that can learn hierarchical representations of action plans, essentially, or control in general. And this can be applied to dialogue systems as well. So we could imagine architectures of dialogue systems where, so kind of like equivalent of LLMs, but are non-autoregressive, in the sense that you give them a prompt, that prompt gets encoded through an encoder that goes through a predictor that predicts the answer. But then it predicts an abstract representation of the answer. And then what you do is you infer the actual answer through planning. So the yellow box is basically the actor, and it performs an optimization of those variables z to find a value of this sequence of representation of embeddings that minimize the cost, the task cost, as well as the guardrails. And once you have a representation of the answer, you run it through an autoregressive decoder that turns it into a sequence of words or tokens. Okay, that part is autoregressive, but it doesn't need to be kind of long-term autoregressive, so has a chance of not diverging and hallucinating as much as current LLMs. So this is a proposal. We haven't made this work yet, but I think it would be really useful because you wouldn't need to do things like reinforcement learning through human feedback. You would need to do this kind of stuff to train perhaps the guardrails or perhaps the cost, but the rest is basically can be trained separately. You can train the encoder, you can train the autoregressive decoder completely separately, and then train the cost and the guardrails also separately. So if all the systems there, if all the modules are differentiable, again, you can do the inference in Z using gradient descent, essentially, right? Gradient-based optimization. And by the way, this is very similar to what people have been doing in optimal control for 6 decades now, called model predictive control, right? So if you're NASA and you want to, I don't know, compute the trajectory of a rocket to rendezvous with the space station, basically you do this kind of computation of imagining a sequence of actions and then shooting the virtual rocket by simulation and then realizing it doesn't meet the space station, so you measure the error between the state of the rocket and the position and velocity of the space station, and then you backpropagate gradient. That's called the adjoint state method or co-state method, and then adjust the command parameters, thrust and orientation, etc., so as to minimize this distance. And eventually, what you get is a sequence of controls that will take you exactly to the space station. So this is a very, very old idea. I'm not proposing anything new here, other than we're going to learn the world model, and it's going to be a lot more sophisticated than just a few equations of a rocket. Okay, so this is what I just talked about, model predictive control, which is kind of a special case of the general architecture I showed. And people have been playing with this kind of stuff in the context of robotics, where the world model is learned. Interesting work by Danica Hafner, for example, at DeepMind, University of Toronto and Berkeley, Chapeau in various contexts, at FAIR in particular, A lot of people at Berkeley have been working on this. Michael Enaf is a former student of mine who is now at FAIR. So very interesting work there. But currently only in the context of control, not so much, on robotics, not so much in the context of reasoning, LLM, and things like that. But it's, planning and reasoning basically can be reduced to optimization, essentially. Okay, so how are we going to train and build and train this world model? And we have to think about, how babies learn in the first few months of life. So babies accumulate an enormous amount of background knowledge about the world in the first few months of life. Things like object permanence, the being able to distinguish biological motion from inanimate objects. Identifying natural categories of objects without being told the name of anything. And then things like intuitive physics, notion of gravity, inertia, things like this. So a 6-month-old baby has not yet absorbed the notion of gravity. So if you show the little scenario here on the left to a 6-month-old baby where there's a car on a platform, you push the car off the platform and the car appears to float in the air. 6-month-old baby will barely pay attention to it. A 10-month-old baby will look at it very, very surprised, like the little girl here at the bottom, because by then they've learned that objects that are not supported are supposed to fall. And so this violates her internal world model, and therefore she pays attention. When your world model is violated, you need to pay attention because you could get killed. And you're going to learn something, most likely. Okay, so we're missing something really big in AI. And the reason one evidence that we're missing something really big is that, we have autoregressive LLM that can pass the bar exam, which is basically smart information retrieval. We don't have anywhere near the type of technology that would be necessary to allow a domestic robot to clear the dinner table and fill up the dishwasher. And it's not that we can't build a robot. It's just that we don't know how to train it to do this, or at least not without enormous engineering efforts and ridiculous amounts of data collection. Whereas any 10-year-old can learn to do this within minutes. The first time a 10-year-old will learn to do this, we'll probably do it. We still don't have level 5 autonomous driving, right? And any 17-year-old can learn to drive a car in about 20 hours of training. So what that means is that we're really missing something big in the ability of a machine to exploit their background knowledge to learn new skills and to acquire this background knowledge about how the world works. That's what we're missing. So we keep bumping into this Moravec paradox, right, which says that things that are easy for humans are difficult for AI and vice versa. This is really true. It's still true. Autoregressive LLM are very fluent. They can write complex text. They can answer complicated questions that require a lot of background knowledge. But in fact, that background knowledge is relatively simple relative to the knowledge of the physical world. Okay, so let's say we're placing ourselves in the situation of trying to train a system to predict what's going to happen in a video. If you use a naive approach, it doesn't work very well. So let's say take a large convolutional net or something, or a transformer, and train it to predict what's going to happen in a video, whether it's a real video like at the top, or whether it's like this is a top-down video of a highway following a particular car in the center. What you get are blurry predictions, because if you ask the system to make a single prediction, the best thing it can do is predict an average of all the possible outcomes that may happen. And that's not a good prediction, right? So if you train the system to make a point prediction, it's not going to work for video prediction. And this is stuff that we've tried for many years. Like the first paper on this that we had was in 2016. We had some colleagues that worked on this in 2015, actually. So the solution I have to this problem is what I call joint embedding predictive architecture. So there's two types of architectures you can use to capture the dependency between two images or two segments of videos. The first one is a generative architecture. So what is architecture? It's one that observes the observed variable x, run this to an encoder, and here something that's called a predictor, which is really a decoder, and then produce a prediction for y. Y is the continuation of the video or the other view of the same scene or a distorted version of the image or something like that, right? So it's generative in the sense that you measure the error in the prediction in input space, in Y space in this case, okay? So what this generative architecture has to do is make a precise prediction of all the details of Y. And that's okay if Y is a discrete variable. If Y is a word, you can't predict exactly which word follows a piece of text, but you can compute a distribution over the discrete set of possible words or tokens that may happen. Typically, it's on the order of a few tens of thousands. Okay, very easy to do. You manage the uncertainty by just predicting a distribution over all possible outcomes. You cannot do this when the prediction is a prediction of a video frame. We do not have a softmax over video frames. And so you could say, well, okay, we're going to encode some sort of distribution over video frames. But basically, after 6 decades of research, nobody has figured out how to do this properly. So I'm proposing to kind of completely get around that problem and not actually predict all the details in the video frame. So the example I used this morning, let's say I take a camera and I start filming the right part of the room and I move to the left and I ask the system to predict, you know, what's the continuation of the video. There's no way, absolutely no way, the system can predict the details of how everybody on the left side of the room looks from what they look on the right side. You cannot predict age, gender, hairstyle, color of clothes, nothing like that. Like how many people fill the chairs, how many rows. That's basically impossible to predict. And then there is other details that are impossible to predict, like the fresco in the back. There's no way my system can predict this. If we were outside, you know, there's a bit of wind, the leaves on the trees would be moving, and that's kind of pseudo-random. There's no way my system would be able to predict the motion of the leaves. So there's a lot of details about the world that we cannot possibly predict, either because they're random, or because we don't have the information, or because they're predictable, but, you know, I mean, they're deterministic, but unpredictable, essentially. So what I'm proposing is this joint embedding architecture, or joint embedding predictive architecture, rather, where the Y variable itself is encoded to an encoder, and this encoder eliminates all the information that is impossible to predict, right? So basically, I'm now training the system to make predictions in this representation space. But now the challenge is, how do we train an architecture like this in a proper way so that it learns good representations of the inputs, but at the same time learns a appropriate prediction. And unfortunately, to do this, we have to abandon the whole idea of probabilistic modeling. We have to use something called energy-based models, which I've been advocating for a long time. What does that mean? So energy-based models is basically the idea of capturing dependencies between variables through the help of an energy function that is supposed to take low values. So it's a scalar output function, scalar valued. And it takes, let's say, 2 variables, x and y. And it's supposed to take low values when x and y are compatible. So let's say when y is good continuation for x. And higher values when y is not compatible with x. Okay, so let's imagine the little diagram here on the right, where the dark disks indicate data points, let's say. So this is my regions of high data density. And I want my energy function to have low values in those regions and higher values everywhere else. Okay, so it could be that for a single x, there's multiple y's that have low energy, which means now I don't insist to make a single prediction for y. I don't insist to make a probabilistic prediction for y. I'm just saying I want my system to have captured the dependency between x and y so that when y and x are compatible, it gives me low energy. When they're incompatible, it gives me higher energy. Okay? It's a much weaker demand than probabilistic prediction. And because it's an implicit function, basically, there might be multiple y's that are compatible with a single x, and so I don't have the problem of having to predict an average of all the possible predictions. Okay, now how do you train an energy-based model? There's basically two classes of techniques, and every learning algorithm you ever heard of belongs to one of those two. Most of them belong to the contrastive category. So contrastive category, I apologize for the quality of the animation on the right, I'm not sure what's wrong, but if you're not careful, if you want to train an architecture like this, like the one on the right, and you're not careful, you're only trying to minimize the prediction error. The system is very happy to produce Sx and Sy that are constant. They completely ignore X and Y. And now the job of your predictor is trivial. It just produces a constant Sy for a constant Sx. Okay? That's called a collapse. So this collapse gives you zero energy for the entire space of Xy, because no matter what value Xy you give to the system, the prediction error will be zero. Okay, so that's called a flat energy surface. That's a really bad way of capturing the dependency between two variables. So it's easy to make the energy small for training samples. You just tune the parameters of your energy model so that the output is low for the X and Y that you observe. What's hard is to make the energy high for regions you don't observe. Okay, so here come the two techniques. The contrastive method consists in generating those green flashing dots, which are outside the manifold of data, and then pushing their energy up. Okay, so you tune the parameters of your energy function, which is some big neural net, so that the energy of the training samples is low and the energy of the contrastive samples is high through some loss function. And then there are another class of techniques that are called regularized method that basically try to minimize the volume of space that can take low energy. Let me go into more details about this. So again, two categories of methods, contrastive methods. So the contrastive method have a flaw, which is that as the dimension of the space increases, the space of Y in particular, the number of contrastive samples you're going to have to generate to train your energy function to have the right shape grows exponentially. If your energy function is infinitely flexible, that's not good. The regularized method, on the other hand, what you do is you add a regularization term so that the volume of space that can take low energy is minimized. How precisely to do this? I'll tell you a couple methods in a minute, but basically there you don't need contrastive samples anymore. It's basically a regularizer that just makes the energy higher wherever you need to. So I'm asking you to abandon generative models in favor of joint embedding architectures, abandon probabilistic modeling in favor of energy-based models, abandon contrastive methods in favor of regularized methods. Of course, abandon reinforcement learning. I said that for many years. Use RL only when planning doesn't yield the predicted outcome to adjust the world model or the critic, but otherwise, don't use RL as much as you can because it's so damn inefficient. Okay, so here are 4 of the most popular pillars of machine learning at the moment, and I'm basically asking you to put them in a can, a trash can. I've attempted to do this before. It took 20 years. I mean, to tell people to abandon popular methods. So I realize this is not a very popular opinion, but I don't see any alternative at the moment. Okay, so there is several types of those joint embedding architectures. Simple ones, we used to call them Siamese nets when the two encoders used shared weights. There is the one that has a predictor, and then there is the ones that have a predictor with a latent variable in case the prediction cannot be done deterministically. And to train those, you need to basically, so essentially what I'm talking about this is because this is the basis of a world model. If you want to have a system that has a world model, it will have to have an architecture kind of like this, where X is the current observation, Y might be a future observation, Sx is a representation of the state of the world, Sy is the representation of the future state of the world, A is an action you might take, Z is a set of latent variables that represent your unknown, everything that's unknown about the world. D is the prediction error cost function, and then C may be some sort of other cost function that you want the system to also minimize because you want to constrain it to pay attention to particular types of data. Okay, so how are we going to train those things? here's a proposal. So the problem we have to correct is the problem that SX and SY can collapse and basically be completely non-informative. So we're going to use a measure of information content, and we're going to maximize that, okay? So we're going to have two cost functions for training, in addition to the prediction error and perhaps a regularization for the latent variable, which I'm not going to talk about. But those two cost functions are this minus I of SX and minus I of SY. This is a measure of information content of SX and SY. And we want to maximize information content, so minimize minus SX and minus SY. How do we do this? It's not easy. In fact, it's pretty much impossible. And the reason it's impossible is that we have ways to measure upper bounds on information content. We do not have good ways of measuring lower bounds on information content. And we want to maximize the information content. So what we would need is a lower bound so we can push up on it, right? But in fact, we don't have any of that. We only have upper bound. So we're going to push up on the upper bound on information content and cross our fingers that the actual information content is going to follow. And magically enough, that actually kind of works. But really, it's not very well justified theoretically. So what are we going to do? First, we're going to make sure that those variables don't end up being constant. And one easy way to do this is you plug the standard deviation of each component of SX and SY into a hinge loss that says, I want the standard deviation to be above 1, let's say. Okay? So what this cost here is a value applied to 1 minus standard deviation of one particular component of SX. And that's going to make sure they don't collapse. This is measured over a batch of samples. It's not enough, though, because the system could end up basically making all the components of SX very correlated with each other or equal. So what you have to do is also decorrelate them. Okay, so the second term in the cost is a covariance term that basically says, I want to make the off-diagonal term of the covariance matrix of the vector SX measured over a batch as close to 0 as possible. The cost is actually the square of the off-diagonal covariance matrix. The sum of the square of the off-diagonal terms of the covariance matrix. And that's not enough still, because now you can get components of SX that are non-constant and not linearly correlated, but they could still be dependent. So another trick is to insert an expander. It's a neural net, trainable like the rest, with multiple layers, which expands the dimension. And it turns out when you train this with this criterion, it makes the component of SX more independent. They're not completely independent, but they're more independent than they would if you just decorrelate them. And we have some theorems about this. There's a lot of very similar method by Yann, for example, at Berkeley. He calls that MCR squared. And then an ancestor to the method I'm recommending that we call VicReg, variance invariance covariance regularization. The ancestor of it is Barlow twins, which was kind of a slightly different way of doing it, but it's very similar in many ways. That's from 2021. And we can use this technique to pre-train an image recognition system. So what we do is we take Y, we corrupt it in some way, we show it to X, and then we try to train the system to predict the representation of Y from the representation of X. Typically, this is done by data augmentation. So you take an image, you distort it in some way by changing the scale, the frame, the colors, whatever. Train the system using VicReg, and then remove the expander and use the representations that are learned as input to a linear classifier, train this linear classifier in supervised mode on a downstream task like ImageNet, and then you get some results. And the results you get with VicReg are, of the same order, like in the top pack of other self-supervised learning methods that are based on different principles, like SWAV and Dino and MoCo and BYOL and similar things, SimClear, which is a contrastive method. And you get features that work really well for transfer learning in object detection, for example, or localization segmentation. In fact, we have an improved version of VCRAG called VCRAG-L that trains local features, not global features for an image, but local features simultaneously with global features. And this one works really well for segmentation. So it gets kind of state of the art for SSL method for segmentation simultaneously with recognition on both. Okay, this is a recent paper at iClear that shows there is actually a duality between contrastive method and methods like VCRAG. So VCRAG actually is a contrastive method, but the contrastiveness is not on the samples, it's on the components of the representation vector. If you think about it, when you want to decorrelate two variables from a vector, you're trying to make those two vectors of activity over a batch orthogonal to each other, right? So you have a matrix of activation. Each row is a vector for a given sample. Okay? Each column is a particular variable over a batch of samples. If you want to, VCRAG basically tries to make the covariance matrix of this matrix. So this matrix transpose times itself equal to the identity. So what it tries to do is decorrelate the columns of that matrix, okay? Make them orthogonal. Whereas contrastive methods like SimClear and Siamese nets and other methods attempt to make the rows of that matrix orthogonal, which is why you have to use very large batch for them to work. And there's a duality between those two methods, but I'm arguing for the fact that ultimately the component contrastive method are more efficient than the sample contrastive methods. But here is another method, which is neither of those, called IJEPA. This is a very recent paper. It was presented at CVPR just 2 weeks ago. Or was that even last week? 2 weeks ago. And this idea is based on masking. So there is no need for data augmentation. You take an image, you run it through an encoder, and then you mask part of the image. You don't mask the image itself. You actually mask features at some level in the network. And you run this partially masked image through the same encoder. So you're going to get partial representation, and then you train predictors to predict the representation of the full image from the partial representation obtained from the masked, partially masked image. So there's a trick there, which is that you kind of share the weights between the encoder at the top and the encoder at the bottom, but with what's called an exponential moving average for various reasons. And this is the main author here is Mido Asran, who is a research scientist at FAIR in Montreal, but this large cast of characters from FAIR in Montreal and in Paris. And this works amazingly well. It's very fast. It works really well. You get really good results on the standard protocol for self-supervised learning applied to things like ImageNet, for example. So what's amazing is that you get something like 81% on ImageNet by just training a classifier on top. You don't need data augmentation for it. This beats masked autoencoder, which is a generative method, and it beats all the methods that use data augmentation, like knowledge about images that allow you to do data augmentation. Here, we're just using masking. So it's really pretty interesting. Perhaps this is one step towards kind of a general recipe for self-supervised learning from images and perhaps video, which is what we're working on at the moment. So ultimately, you want to use a system like this in a hierarchical fashion. And there's another piece of work, which is to train a system from video to learn hierarchical representations that allow to make predictions in video. And so that system has an encoder, which is trained simultaneously to using VCRAG to produce good representations using data augmentation. So invariant representations if you want, but at the same time, it's also trained on successive video frames to predict what the next video frame is going to look like from the previous one. And it's using a really complicated architecture that I don't have time to describe, which basically is based on sort of warping feature maps and representation to obtain a representation of the bottom frame from the representation of the top frame. But it's really a hierarchical JEPA type architecture. And this system can really do a good job at learning representations of things like making prediction of optical flow, as well as learning representations that do a good job at for object recognition. Okay, so perhaps this is a recipe, or at least the embryo of a recipe for learning hierarchical world models from video. Perhaps we're going to be able to use this in the context of dialogue systems in relatively short order. And we need to make progress in self-supervised learning. We need to handle uncertainty in prediction using those joint embedding architecture, not generative architectures, at least not for images. We can use this to learn world models from observation, and perhaps we can use them to do reasoning and planning. So that's my plan for the next 10 years until my brain turns into white sauce. And what's interesting about those is that, is this a path towards human-level intelligence? I don't know, but I'd be happy if, by the end of my career, which is coming soon, we get to the level of a cat intelligence, maybe a dog, and perhaps, that would be an indication that we can go further because the architecture is not that different between cats and dogs and humans. Common sense is really a collection of world models, not just knowledge. Reasoning is really optimization and planning. Understanding is really prediction using world models. When we learn, we change our mental model of the world. That's really what we do. And one problem we're going to have is designing intrinsic cost functions that drive learning and that drive behavior so that it's safe. And I'm going to stop here. Thank you very much.
So thank you very much, Professor. I personally found the talk very, very interesting. We have now, I think, 10 minutes more for questions. So are there any questions? Okay, we can start over there. Do you need a mic or? No, I think you are good. Okay. Okay, let's use the mic.
Thank you very much for the very interesting talks and all the ideas, even if controversial sometimes. This is what we need, I think. A couple of thoughts on guardrails and safety. So I was wondering how you see guardrails as being implemented. Are they part of the decision-making function, like perhaps it's been proposed in agent-based computing? Are they symbolic elements? Are they particular weights in the decision-making? So that would be question one. And question two regarding safety. So in many areas of software engineering or where we're building complex systems, I have Dragos next to me, builds airplanes. Safety is something which is assessed from the outside. Yeah. Clearly there is something inside the system which will ensure that the system is safe, but then we go outside and we take a bird's eye view and do perhaps automatic verification, and we are able to say, under these conditions, the system is safe, and that also serves as sometimes as a certification. Do you see also this component as part of the safety argument, or is it only something that lives inside the agent? Thank you.
No, I do see this as part of, I completely agree with you that the safety assessment and the safety system to be somewhat external, but that is in fact what I'm proposing, that the objectives are separate from the main system essentially. And they are components that might, for example, ensure that whatever the system makes a prediction using its world model, the state of the world model stays within the region where the world model is reliable. Because it could be that the world model, has not been completely trained on the entirety of the entire state space. And so when you go into a region of state space that you have not explored, the predictions are unreliable. So you can put this in a guardrail, say don't go into that part of the space, you've never explored it before. Or on the contrary, when you're in learning mode, you're telling the system, go into those part of the space where your predictions are bad because that's the way you train your world model, right? So that's like play, right? Or curiosity-driven learning. But yeah, I think the guardrails, so there's two types of guardrails. The best ones are guardrails that you can, there's three types really. The best one is the one you can just write down as a differentiable function. So because they're differentiable, you can optimize them with respect to the plan, the outputs, essentially, or the internal representation you're doing planning in. But that's probably unlikely that you can do that. So the second best thing is to train a cost function, guardrail or otherwise, so that it maps from an internal representation to a cost, right? And if you have a hardwired programmed cost function, doesn't need to be differentiable, that you can measure, you can also run it through your system, and then your system will compute its internal state, and then you can train its intrinsic cost to predict the value of the guardrail, and then use that as a differential model for the guardrail. That's very much the same thing as a critic in RL, or what people now call a reinforcement model, a reward model, basically, right? It's a differentiable approximation of a cost function that you can measure, but you don't know the form of it, right? And then the third form would be something that's completely trained through human feedback, for example, so that which is basically what people are currently doing with LLMs, right? You give it an input, you have it produce an output and multiple outputs, and then you have them being rated by people or proposing a better one, and then you train a reward model, which to make that prediction. So currently, what LLMs do is that they use this reward model as a cost function used for training the system. Here, I'm using it as a cost used at inference time, which is very different. It's maybe more expensive at inference time, but it's much safer, because if you use those guardrails at training time, there is no guarantee that the prompt will not completely go outside of the distribution of the training set, and therefore you're going to hit a situation you've never encountered during training, and the system is going to jailbreak. Essentially, that's what jailbreaking is for LLMs, right? If you use those guardrails at inference time, there's no way the system can escape the guardrail. So that's how you make safe AI systems. And I think a lot of people were worried about the dangers of AI system. Imagine that they're going to be autoregressive LLMs, and they say, oh my God, those things are going to be horribly dangerous if they get intelligent. They're right, but we shouldn't keep them. My prediction is that 5 years from now, nobody in their right mind would use autoregressive LLMs.
Thank you.
We have a question over.
Hi, Frank van Harmelen from Amsterdam. Thank you very much for an inspiring talk. So I'm going to try to make a link with cognitive science, right? So would you agree that there's two important analogies here? One is that cognitive science tells us we're not end-to-end learning from pixels to actions. It's mediated by internal world models. And that you embrace. And that your JEPA models are very much like the brain as a prediction machine, right? Which is, I think, more or less now the dominant paradigm in cognitive neuroscience. Is predicting the next state of the world.
Sure, yeah. I mean, there is a lot of models that come from computational neuroscience and system neuroscience that have a bit of the same motivation. So certainly, active inference, for example, from Carl Friston, the way the actions here are inferred or the representations are inferred, this is very much active inference. In fact, the symbolism I use is the symbolism of graphical models, of factor graphs, right? My cost functions are squares, my variables are round, and then I have this extra symbol, which is kind of a rounded shape that is supposed to represent a deterministic function, which classical models don't have. But it's very much the same thing. And then, of course, the idea of training a system by prediction is predictive coding, right? Which is kind of a popular concept in neuroscience.
Okay.
Yeah.
Thank you.
One question over here.
Thanks, Yann. That was a fantastic talk. I just was wondering, I mean, throughout your presentation, one of the most important factors is cost. I mean, to a large extent, we are taking a very high-dimensional problem and reducing it to a small, low-dimensional sort of problem such that we can compute some kind of a cost. Isn't cost sort of designing the cost function, to a large extent, very important? I mean, in your the proposal that you mentioned as well, the cost is something that you're manipulating to a large extent.
Yeah, I mean, designing cost is non-trivial, but consider the alternative, which is to design an entire control system from scratch. So, the same way you could imagine building a computer vision system by designing it from scratch, without any learning, okay? Or you can design a parameterized architecture, like say a convolutional net or a transformer, and then design a cost function that should be minimized with respect to the parameters of this architecture. And we know for a fact the second approach actually works, and works much, much, much better than the first one, right? Because despite what we think our engineering abilities are actually very limited, so we could never come up with a completely engineered solution to the computer vision problem. Whereas if we use learning, it works really well. So it's the same story here. We don't know how to design intelligent machines, but it's probably a lot easier to design and specify cost functions that this machine is supposed to optimize, not just at training time, but also at inference time, which is essentially what I'm advocating for. Another point that's important that I forgot to mention is that when you have an inference procedure that works by optimization, so if the output of the system is computed through an optimization process that may have an unlimited number of steps, this is Turing complete. It has the power, general computing, essentially. Whereas if you have a system like an autoregressive LLM that produces one token after the other, every token takes a fixed and limited number of computational steps to be produced, right? ChatGPT has, 48 or 96 layers in its LLM. You go through those, n layers, you produce one token. Go through n layers again, produce the next token. So you cannot have a different amount of resources allocated to a more difficult problem than a simple problem. You can allocate more resources to a more difficult problem is to ask the system to think step by step so that it will actually produce more tokens, right? And so it will spend more computation. But that does not have Turing completeness possibility because you always have a finite number of computational steps per token. So I think, we have to think about those things. It's the same kind of general back in the old days with neural nets that, yes, you can approximate any function you want with two layers, with a two-layer neural net or a kernel machine or something like that. But it's going to have to be very inefficient because we know there are a lot of functions that are very hard to compute with just two steps of nonlinearities. So having layers is obviously very interesting. And it still never ceases to puzzle me that it took 15 years to convince people that that was the case. It's a completely obvious statement that people were completely blind to. So I think there's kind of perhaps a similar type of statement you can make, about autoregressive prediction versus inference from optimization.
Thank you very much. I think we can close it here and yeah.
Thank you.
Okay, we have one more step before the coffee break. So please stay seated. Wait one more second. Thank you again to Yann for a super interesting and topically very fitting lecture. Really nice, thank you. We have one program item, namely 2 challenge presentations. So one of the things I take away from Yann's presentation is that our context here can give an opportunity for confluence between different research fields and different research lines, from computability theory up to supervised or self-supervising learning. And one of the things which I think we've learned in a couple of other fields over the last years is that it's sometimes hard to crystallize research into one focal point. So you have people who are working on connected topics for a long time, but somehow they never meet, or at least somehow, even if they meet, they have a hard time comparing what they've been doing. And one of the concepts which work really well to catalyze these moments are challenges. Yeah, so for the first time at an NeSy workshop, unless Arthur now forcefully corrects me, we this year have 2 challenge announcements, one by Eleonora and then one by Marco. Stage is still yours.
Thank you. So, hi everybody. I just want to quickly present a challenge. This is actually a NeurIPS 2023 challenge, and it's probably the first Neural-Symbolic challenge that will be hosted at NeurIPS. And the title is RODAR, the Road Event Detection with Requirements Challenge. And it's very much connected to the concept of guardrails, like you were talking about. So I want to give you first just a very brief introduction of the dataset itself. So the dataset, some of you might know, is an autonomous driving dataset. It's annotated with road events. What is a road event? A road event is a series of bounding boxes linked in time. And each bounding box is annotated with a set of labels. What are these labels? The agent labels, the actions labels, so what are the actions that the agent is doing, and the location labels, so where is the agent. So for example, you can see here we have a pedestrian, which is labeled with pedestrian, moving away, and it's on the left pavement. What is the peculiarity of this dataset? Well, the dataset comes also with 243 requirements expressed in propositional logic, which asserts which set of labels can be associated with each bounding boxes. So, for example, we can have not move away or not move forward, which simply states a very basic reality of our world. Something cannot move away and move forward, like from the autonomous vehicle itself. So, given this data set, we have two tasks. The first one is we give you a partially labeled data set, and we want you, ideally, to use the background knowledge that is encoded in the requirements themselves to give your best prediction. So whoever does the best predictions wins, okay? But you can only use a very limited amount of labeled data. The rest will be considered unlabeled. The second task, on the other end, will give you like a fully supervised data set. So you'll have for each frame, all the bounding boxes, all the set of labels. But here, you will give us a model that makes predictions that are always compliant with the requirements. So no matter what we give you, your model will need to give us predictions that are compliant. So we'll need to implement some sort of guardrails. There are obviously some prizes. So obviously the winners of both tasks will be invited to go for the NeurIPS 2024 paper. So how this works is that NeurIPS sort of forces the organizers of the competitions to submit a paper, and whoever wins will go for it with us. And secondly, I've asked Arthur, and he seemed to agree, but we can invite all the participants of the challenge that managed to obviously beat our baseline model to submit a paper to the new Neural-Symbolic AI journal. And finally, we have also some monetary prizes awaiting for the winners. We have more than currently 4K up for grab. It might increase if we manage to secure more sponsors, but let's see. Finally, since this is a very heavy task because it's with videos, if you have some problems in not being able to have computational resources, we also give away some mini grants of around $200 for computing units. So if you want to know more, just visit the website over here. And obviously, we are open to questions, and you can send me an email, and I can answer whatever you need. Thank you very much.
If you happen to have an industry affiliation and think this type of project is worthy of your support, they still accept sponsorship.
Oh, yeah.
Just mentioning.
Okay, thank you. So just to start, Eleonora just mentioned prizes you can get with our competition. We don't have money. We have T-shirts. If you visited the cloister just beside this room, there is a stand with some collaborators who are inviting you to participate to this challenge. Let's call it challenge. Better is a project we started on automated crossword solving and generation. Basically, as you know, games are a testbed for many AI algorithm. And crosswords are something that unifies different capability of humans, like constraint, satisfaction, and natural language processing. So I think everyone knows about crosswords. And we started this project almost 20 years ago with WebCrow. That was the first system that was developed to solve crosswords by applying natural language understanding and grid filling capabilities. What we are doing right now is to revive this project into its second version. As you see, it's WebCrow 2.0. So basically, we are offering a platform that is able to integrate modules that are able to accomplish several tasks that are needed to solve a crossword. And we designed this system to be cross-lingual, scalable, open, and the last part is devoted also to generate crosswords. So this is I don't want to spend much time, but this just show you the general architecture of the system. As you see in the middle, you can add modules in the platform that are based on NLP techniques, web search, and so on. And then you have to merge the list that are candidates produced by the single experts in the system and to fill the grid. This is just another, I would like to go directly to generation. So what you can try here are some crosswords that were specifically generated for this conference automatically. And the goal for continuing this project is to have an AI-assisted generation of personal crosswords. That means you can specify a topic, specify the pattern of the crossword, and also the difficulty, and the system would assist an author to generate this. The possible goals for this is for entertainment, but also for educational purposes. We are going to experiment this in the university with some courses where the teacher can provide a document describing the matter is teaching, and the system will generate and propose some crossword that the student can use to learn, for example, specific lexicon for a given matter. So if you are interested, this is the team that is working on this, me, Professor Gori, and other PhD students, and we have the sponsorship of Expert AI, that is a company in Italy working on natural language processing. So if you are interested, we will provide both the library that is for crossword solving, and we have a huge data set of clues for crossword, both in English, Italian, French, and maybe German. Okay, thank you very much.
Thank you, Marco. So 2 minutes left to the coffee break. You will get 1 minute of those, but before that, poster presenters and people in the first poster session, please use the coffee break to already mount your posters. They are to be mounted out where there was lunch, like in that space. Secondly, I'm still missing 2 poster pitches. You aren't obliged to use slides, so if you want to free wing it, fine by me, just don't complain afterwards. Thirdly, the 16 poster pitch presenters, strategic advice. You want to be seated in the front rows when we reopen, because your way to the podium and back counts into your 1 minute 45. And we're going in the order in which you appear in the program. Let the games begin, but before that, coffee break. Thank you.